example that we will consider a finite state machine. So, in this case we are considering a lock that has got a digital input to unlock it, and the input is 101. So, that is there is a single input to this lock. So, conceptually you can think of it as a lock like this, and it has got a B input, and this B input is serial, like so if it sees the sequence 101, then the lock will be opened. And once so every 101 sequence is different, like say if I press this sequence 101, then the lock is open. But after this lock is open, so it will go to a lock close mode, and after that it will require another explicit 101 sequence for turning it on or opening the lock. So, we will see that. So, the state transition diagram that we have is something like this. So, initially we are at in this in the first state, where you see that we have we can say we have seen a 0. As long as we see 0, we stay in this state. So, we let us call the name of the state as 0 scene, and then when it is in the state 0 scene, the output is 0. So, lock is not open. So, as long as we are getting B equal to 0, so we continue in this state. Now, B equal to 1, so this comes, it takes us to a state which we name as 1 scene, that is our unlocking pattern is 101. So, we consider that we have seen the first 1 in that sequence. So, then also the output remains 0, that is the lock is not yet open, and as long as B remains equal to 1, so we continue to be in this state. So, you see that the sequence may be like this, somebody may be entering values the 1 1 1 1, then 0 1. So, as long as these ones are going, so it will remain in this state 1 scene, and then after that when this and the output remains 0. Now, if the B input becomes 0 after that, so it comes to a state which we call 10 scene. So, after in this 10 scene state also the output remains at 0, the lock is closed, and then if we get a 1, then it is 101 scene, and when it is 101 scene, then the lock output is 1, that is lock is open. Then after if we get a 0, then it goes to 0 scene state, that is lock becomes closed, and we are in the state as if we have seen a 0. And if B equal to 1, so this is a new unlocking sequence that I was talking about. So, B equal to 1, so it takes us to this state. So, again you need another explicit 101 for unlocking the lock. So, if you press B equal to 1 or B equal to 0, the lock becomes closed. So, lock is so you can say that as if the lock is closed, and then this again another 101 input sequence is necessary for unlocking the lock. So, B is the input signal to the lock, and X is the output signal of the lock. So, you can say that box that that I had drawn, the lock box. So, B is the input and X is the output. So, whenever we see 101 in B, the lock is turned open. So, we can say that the state transition can be like this. If we name these states first state as 0, the code of the state is, or if we make that the code of the state is 0 only. So, this first state is coded as 0 0. If B equal to 0, the next state is also 0 0, and X remains equal to 0. If B equal to 0 and the current state is say 0 1, then the next state becomes 1 0. Okay. So, if we are at state 1, so this we code as 1. So, we will come to this coding part later. So, there are 4 states. So, in this particular case, it is assumed that this state is coded as 0 0, this state is named as 0 1, this is 1 0, and this is as 1 1. So, if the input state bits are 0 0 and the input is also 0, then the next states are also 0 0. So, this is the first transition. Second transition says that if the current state is 0 1, that is this one, and the input is 0, then it remains in this state only. So, sorry, yeah, it remains in this state only. So, it goes to the state 2. So, 1 0. So, if this is 0 1 and B is 0, then it is going to the state 1 0, and the output remains 0. So, that way we can make this full table, and once this table has been made, so we can do a simplification and get the next the combinational logic for doing this thing. So, this x is given by H0 L0 and this or x H0 L0. So, Hn is given by this function and Ln is given by this function. So, we can just make a combinational logic and we can say that we can put this combinational logic into some part of the circuit. So, this is the combinational logic. So, it has got B as one input, then H0 and L0 as other two inputs, and then we have got these two flip flops which holds the H and L, which are H and L values. So, this H next and L next. So, they come here and they are fed to, let us name this as H0 and this as L0. So, this L0, so H0 is fed here and L0 is fed from this point, and then this is our x output. So, in this part, so we realize the function for x equal to, then Hn equal to and Ln equal to. These individual functions are realized in this part. So, I am not drawing the combinational part there, but it can be realized using that. Next, we will be looking into another example which is a shift register. So, this is the standard shift register that we have. So, as you know that with the input of every clock pulse, this input bit gets shifted through this D flip flop chain. Now, once this input pattern is known, so you can try to draw the corresponding finite state machine. Now, we really do not know like what is the initial state of these 3 flip flops. So, it can be any of the states 0 to 7. So, if we if we assume that the initial state is 0 0 0, then if the on the arrival of the next clock, if that at that point of time is n equal to 0, so it remains in this state. If n equal to 1, it goes to this state 1 0 0. Similarly, if the current state is 1 0 0 and the next input is 0, then it comes to the state 0 1 0, because this one gets shifted here and the 0 from the input comes to the first flip flop. So, this way you can complete this total finite state machine, which will so from the circuit. So, this is the other way. So, from the circuit we can come to the finite state machine. So, here no other combinational logic will be necessary, because this if you simplify this particular machine for the state transition function and output function, you will find that it gives rise to the function like, say this is Q2 equal to D2 equal to Q1, D1 D3 equal to Q2, like that. So, it will come in a simple fashion like that. So, that is why we do not show the circuit separately, but this is nothing but this connection. Now, how do you design an FSM, finite state machine? So, first thing that we have by this time we know is the description of the finite state machine behavior. So, which is done in terms of state diagram. So, we can have some specification of a system in some English like language, and then we convert that description, that English language description, into a finite state machine, and that finite state machine has got some inputs and outputs. There will be some symbolic states and there will be state transitions. So, we can check whether this description that the finite state machine that we have drawn, it really reflects the finite state machine behavior that was given as input, and that check can be manual, that check can be based on some formal method. So, which is beyond the scope of this course, but that verification can be done. Now, once we are satisfied that our state transition diagram, whatever we have drawn, truly reflects the behavior that has been asked for. So, we go to the next step, which is state diagram to state transition table. So, where inputs are the current state and the primary input. So, they constitute the inputs and the outputs are the primary outputs and the next state. Now, once this from state diagram to state transition table we have drawn. So, next thing is the state encoding. So, every state is given some binary code. Okay. So, we naturally we need to decide, like if there are say 4 binary 4 states. So, if there are say 4 states, say symbolically we represent it as S0, S1, S2 and S3. Now, for 4 states I will need 2 bit code to at least a code of at least 2 bit length to distinguish them. So, somebody may code it like this, that the state S0 is 0 0, S1 is 0 1, S2 is 1 0 and S3 is 1 1. Now, there are other choices also, like you see that somebody may code it like this one as 0 1, this is 1 1, this is 0 0, and this is 0 1. So, there is nothing, there is no restriction regarding the choice that you make for the states. Somebody may even do this coding of higher number of bits, like in this case. So, if I do a 2-bit coding, so if I do a 2-bit coding, then you see, so I can have 4 choices. So, total number of alternatives that we have, like this is alternative 1, this is alternative 2. The number of alternatives that we have is 2 power 2 factorial of that, because this is I can just these 4 values. So, I can arrange in any order. So, any permutation of those 4 states, that is good enough. So, it can give 4 factorial alternatives. And if there are, say, n number of states, so n is the number of states, then the minimum number of bits, so minimum number of bits needed is going to be log n to the base 2. Okay. So, and the ceiling of that. So, this is the value of n that we are talking about. So, this is the this is the small n number of state bits needed. And so, if I do so this is the minimum number. So, there is no restriction on the upper limit. So, we can go for any number of bits which is more than small n. Okay. But if I choose this small n number of bits, then the number of alternatives that I have is 2 power n factorial. So, you see this is a huge search space that is there, and for each of these combinations. So, it is very much likely that the corresponding circuit that you get will be different. So, so basically if we say that so this is the finite state machine, and we have got these flip flops. Okay. So, this is that combinational logic that we have. So, that takes the primary input as primary inputs, and it produces the primary outputs, plus it gets lines from these flip flops, the next state bits or the present state bits. It gets the present state bits from here, and it produces the next state bits. Sorry, let me draw a clear diagram. So, this is the combinational logic, and we have got the flip flops. Fine. So, the primary inputs are connected to this combinational logic. Similarly, it produces the primary output, and these flip flops content. So, they constitute the present state. So, they constitute the present state, and it computes, this combinational logic will compute the next state like this. So, this is the standard technique that we have seen. Now, you see that depending upon the coding, like individual states, what code we give, this combinational logic is going to vary. So, what is the best possible state assignment in terms of maybe the number of gates in the combinational logic, or the power consumption of the combinational logic, and this or maybe some other factor. So, that is a difficult problem. So, there are lots of research works that have come up on this particular problem, which is known as the state encoding problem. We will so come back to this later. So, I wanted to emphasize on this point that there are lots of choices in the state encoding process. The next part is the implementation part. Now, these flip flops that I have said, so I did not explicitly mention which type of flip flop we are using. So, normally while we are doing the design, we use D type of flip flop. So, this is the D type of flip flop, D and Q. So, D is getting the this next state bit from the combinational logic and giving the present state output to the combinational logic. Now, it is not necessary that we have to use D flip flop only. Somebody may say, okay, I will use a JK flip flop. So, I will use a JK flip flop, and accordingly 2 lines should come from the combinational logic to determine the J input and K input for the flip flops. Now, so that is one reason that why JK is generally not used, because of this reason that you need to compute this combinational logic that we have. So, they need to compute 2 functions per flip flop, one for the J input, one for the K input. Whereas, if the flip flop is D, then the next state logic needs to compute only one function for a flip flop. So, as a result it may be easier that we do the realization using D, but that is not always true. It depends, because JK type of flip flop, they offer other transition probabilities, other transition properties. So, that way maybe for some finite state machine JK is doing better, or maybe T type of flip flop may be used instead of this D flip flop. However, in general, in whatever designs that we see, so they use D flip flop because of its simplicity, you can say, and because of this combinational logic design and the CAD tools that have been designed. So, they specifically target it as D flip flop. So, that is why D flip flop has remained as the standard one. Then after this is done, so after these flip flops have been chosen, so we synthesize combinational logic from encoded state table. So, that way we do the full synthesis. So, this is the full synthesis process. So, we will take an example and explain like how this is taking place. Suppose we want to implement a counter that counts in this sequence 0 0 0 0 1 0 0 1 1 1 0 1 1 1 0, and after that it comes back to 0 0 0. So, the first point is to derive the state transition table from the step. First step is basically the state transition diagram. So, in this case it is obvious. So, it starts at sorry, this diagram is something this sequence is something wrong, I am sorry. So, this sequence is not correct. The sequence that it is doing is basically if you start at 1 0 0, then it goes to 0 1 0, then it goes to 1 0 1, then 0 1 1, 0 1 1, and then 1 1 0, and then it is coming back to 1 0 0. So, that is the sequence that it is doing. So, this is so derivation of the state transition function is like this, that if the present state is 0 0 0, then the next state is a do not care. So, the next state for 0 0 0, the next state is do not care. Similarly, 0 0 1 also the next state is do not care. So, what happens if the counter reaches any of these states? So, that is not a not an issue with the designer. So, that is kept as do not care. If you start at 0 1 0, then the next state should be 1 0 1. So, this way the present state next state relationship is done. So, do not care conditions that arise from unused state codes. So, that is basically ignored. Okay, so, this way we can do this state transition table part for this example. Now, after that is done, so we can synthesize the logic for next state functions and derive the input equations for flip flop. So, that way you make the truth table from this you make the truth table from this graph, from this next state table, the state transition table. So, you can make the truth table for C plus, B plus and A plus, and this is the functionality that we get, C plus equal to B, B plus equal to A plus B bar C, like that, and then we can go for realizing the circuit. Sometimes we are looking for some self starting FSMs. So, self starting FSMs, so they have got some startup states. So, at power up, so FSM may be in an used or invalid state, but the design must guarantee that it eventually enters into a valid state. So, this is self starting FSM. So, design the FSM so that all invalid states they eventually make a transition to the valid state, and this limits the exploitation of do not care. Like say, so previously we had say this, while we are writing this 0 0 0. So, we took the next state as do not care, but here that we cannot take. So, 0 0 0. So, we put it as if you start the machine at 0 0 0, it will come to 0 1 1. Similarly, if you start at 0 0 1, so it will come to the state 0 1 0. So, that way it is restricted, but it is not arbitrary, like in the previous example that we have seen. So, there if you start at some state which is invalid, it is unknown. So, what will be the next state? So, that is not known, but in this case it is completely specified. So, this self starting FSM, so they will always either keep you in this cycle always all 1, or it will take you to one of these 5 states, okay, after some time. And going by the same mechanism that we have drawn, so you can draw the state transition table, like say from 0 0 0 it is going to 0 1 1. So, 0 0 0 it is going to 0 1 1. Similarly, 0 0 1 it is going to 0 1 0. So, 0 0 1 it is going to 0 1 0. So, rest from 1 1 1 it remains it is 1 1 do not care. So, from 1 1 1 it can either remain in 1 1 1 or it can come to 1 1 0. So, that way it is left to the designer. The specifier, the specification does not tell what will happen to 1 1 1 clearly, but it can go to either, it can remain either in this state or it can come to this state. So, if that is specified, then it has to be 1 1 x, but if we want to follow this diagram truly, then for this 1 1 1 the next state should also be 1 1 1. Anyway, so once we are done with this state transition table, so we can make the corresponding circuit and get it done. Next, we make a look into a comparison between Mealy machine and Moore machine. So, Mealy machines, they tend to have fewer states because the output is a function of state, present state and input. So, as a result, many of the Moore machine states, so they are they can be combined in a Mealy machine state, because of the reason that for Moore machine, for every even the otherwise the two states being same, only the output being different. So, they are going to constitute two different states, whereas for Mealy machine, so they can be clubbed into one state and we can represent the transitions by means of this inputs also. The input, the inputs, primary inputs, they can also be considered as some constraint on the primary output. Second point is the Mealy machines react faster to inputs. Because of this reason, that in case of Mealy machine, what is happening is that suppose this is the current state and there is a transition like this to this state. So, input slash some say input slash some output. So, if in this state, if the FSM is in this state, then as soon as this input condition is satisfied, for example, if I say that from this state it is going to this state and the condition is A equal to 0, and in that case it will make B equal to 1. So, if the machine is in this state, then whenever A is equal to 0, B will be made equal to 1. So, that is possible for Mealy machine, but in case of Moore machine, what is happening is that this output is a part of the state itself. So, it will be like this, say A equal to 0, A equal to 0. So, it will take to this state where it will make B equal to 1. Now, this transition of state cannot occur until the next clock pulse arrives, because the next state function that the combinational logic computes. So, it is put into this flip flop, and this flip flop output will come to this point only when this clock has arrived to this flip flop, otherwise this value is not available at the output of the flip flop. So, as a result, even if A equal to 0, till the clock pulse comes, the machine does not transit from this state to that state. So, B does not become 1 till the transition has take place, or we can say that till the next clock pulse has arrived. So, there is a delay to the output, depends on arrival of. So, this react in same cycle, do not need to wait for clock, and delay to output depends on arrival of input. Whereas, Moore machines, so they are generally safer to use because our output will change at the clock edge. So, always one cycle later. So, it can be a bit safe in our design. In Mealy machine, input change can cause output change as soon as logic is done. So, sometimes it is a problem, particularly if you have got two machines that are interconnected with an asynchronous feedback. So, one machine making a transition that can affect another machine's operation. So, if it is a Mealy machine type of if it is a Moore machine type of realization, then both these machines will transit at the next clock pulse. So, they are going to behave in a better fashion compared to a Mealy machine, where one of the machine may make some transition in between because the change in the input combination, and as a result the output may become the interconnection, the interface may become problematic. Sometimes this is seen. So, though there is no hard and fast rule like which one will be used, but in general Mealy machine has got less number of states. So, for large machines, so we will go for Mealy type of realization. So, the steps for coming back to the steps for implementing a finite state machine. So, first point is to perform state assignment. So, we can make different assignments that can give different results. There is as I said that it is an NP hard problem. So, there is you cannot solve the problem optimally with a polynomial time algorithm. So, as a result there is no really good heuristics that exists. Then sometimes we use some extra bit, 1 bit or 2 bit extra that makes the combination logic simpler. And the extreme point is with FPGAs where we do one hot encoding. So, one hot encoding is like this, like if I have got say 4 states S0, S1, S2 and S3, then I can say that for S0 I have a code like this 0001, S1 is a code, the code is like this, S2 is a code like 0100, and for S3 the code is 1000. Now, whenever there is a transition from one state to another state in the finite state machine, you see only 2 bits are going to change. Okay, so, only 2 bits are going to change. So, that makes it interesting. So, the combinational logic that we have, so that becomes much simpler since only 2 bits will be changing. So, this type of coding is known as one hot encoding. The one hot means in the state code only 1 bit is 1 and all other remaining bits are zeros. And this is particularly useful when we have got this flip flop rich architectures like FPGAs, field programmable gate arrays, we will see that later. So, this one hot encoding is very popular. So, we convert state diagram to state table, we can do equivalent representation or we can do some, it is a mechanical process, and then we can get the state table truth table for the next state and output functions, and then go for a logic minimization, logic implementation. So, if we look into an example like we are looking into a vending machine. So, it delivers a package of gum after 15 cents have been deposited. There is a single coin slot for dimes, nickels, and there is no change is given back. So, first step is to understand the problem. So, this is my vending state machine FSM. There is a coin sensor that senses nickel and dime, and there is a reset that will reset the system, and there is a clock signal. So, when appropriate change, some 15 cents or more has been given, then this slot opens and one gum is released. So, gum release mechanism is given the open signal. So, that is the specification of the problem. So, you can say that we can, so how can we go to 15? Okay. So, there can be 3 nickels, 1 nickel, 1 dime. So, nickel is equivalent to 5, dime is equivalent to 10. So, this one, so sequence may be 3 nickels, nickel dime, dime nickel, 2 dimes, and we do not give the change, 2 nickels and 1 dime. So, that way we do not give the change. So, whenever it becomes just higher than 15, the gum is released. So, it is we start at state S0. So, this sequence is in nickel, nickel, nickel. So, going to the states S1, S2, S1, S0, S1, S3 and S7, and in the state S7 the open signal is equal to 1, or it may be dime dime going like S2, S6 states. So, we draw this diagram. After this diagram has been drawn, so we look into the behavior and get the confidence that this really represents the behavior properly. Then we do some state minimization. So, all these states that we have drawn here, they are not required and they can be minimized into this thing. So, on reset it enters into a state called 0 cent, and then if the nickel is placed given, then it goes to 5 cent state as if it has seen 5 cent. Another nickel comes to the state called 10 cent, and from 0 cent also if a dime is given, it comes to the 10 cent state. Similarly, from the 5 cent state, if a dime is given, it comes to 15 cent, and from the 10 cent state, if it comes to the state 15 cent. Of course, so this is from 10 cent, if you put a dime also, though it is 20 cent, but we do not need to remember that as a separate state because no separate action is necessary. So, that is 15 cent only. So, after that if we code the states like say the present state is 0 cent. So, 0 cent then if the input given is 0 0, then it remains at 0 cent, that is no input is given and output remains 0. then if a nickel is given, it comes to the state 5 cent and the output remains 0. So, in this way you can draw the symbolic state table. Once you have drawn the symbolic state table, the next part is the state encoding. So, this Q0 present state, so this 0 cent, 5 cent, 10 cent and 15 cent, they are given the code 00, 01, 10 and 11. Accordingly, you get this next state function. Once this state encoding has been done, so we have got this truth table. So, this truth table you can now minimize using some Carnot map for individual D1, D1, D0 and open for the for these three functions you can get. So, this is the function that is obtained, D1 equal to Q1 plus D plus Q0n. So, like that you can find out that this is the function obtained, and ultimately we can realize it by means of some combinational logic function like this. Okay. So, this is the vending machine example. So, in this way given any finite state machine, so you can start with the behavior, come to the corresponding state transition diagram, then from there the state table, and then encode the states using some codes, and then come to the combinational logic to be realized, and then get the final function realized in terms of logic gates and flip flops.